Hey everyone, so we're going to be going over the midterm one practice exam solutions. First, we'll start with question one, which is the heuristics problem. For parts A, B, and C, we're going to be considering the corners problem from the first programming assignment P1. Just to reiterate, if you don't remember, the corners problem was that there was a food pallet located at each corner of the grid, and Pac-Man must navigate the maze to find each pallet. The step cost for traveling between grid squares will be 1 for each action. So for each of the following heuristics that we'll go over, we're going to say whether or not it's admissible. And if it is not admissible, then we're going to give a counterexample that shows that the heuristic isn't admissible in a particular state. So first, we're going to consider H1, which is, let's say it's the maze distance to the nearest food pellet. And if no food pellets remain, then H1 will be equal to 0. So for this question, we can see that this heuristic is going to be admissible for all states possible in Pac-Man's grid. This is because Pac-Man needs to travel to at least the nearest food pellet, and maybe more food pellets if they exist. When there are no food pellets, then that means we've reached our goal, which means that H1 is 0. That represents our goal state, so that's admissible. If we look at the example that's given here, you can see that the distance to the nearest food pellet is 2. And then Pac-Man needs to be traveling to the other 2 food pellets that are not as close as the nearest one. So that cost will be added to the actual cost. So therefore, the heuristic to the nearest food pellet is admissible. Next, H2 is the number of uneaten food pellets remaining. We can also see that this heuristic is admissible. If we look at the distance for Pac-Man at any particular state to any of the food pellets, Pac-Man will need to be traveling at least a distance of 1 so that it can reach a food pellet from its current location. Therefore, if we count that step distance of 1 for each of the food pellets that are remaining, we can see that Pac-Man needs to travel at least that much in his grid, and therefore the cost would be always greater than or equal to the number of food pellets remaining. Next, if we sum up the previous 2 heuristics that we got, where H1 was the distance to the nearest food pellet and H2 is the number of uneaten food pellets remaining, we get a new heuristic called H3. And we can see that H3 is in fact inadmissible. And we can give many different counterexamples for this. I just provided one counterexample here, where Pac-Man is located at this particular location here. The distance from Pac-Man to the nearest food pellet is the distance of 2, and there's 1 food pellet remaining, so the heuristic value would be 3. But the actual cost of Pac-Man to reach the goal is 2 because he only needs to travel 2 steps to reach the nearest food pellet. And once he eats the food pellet, he would pretty much reach the goal state. So H4 is the absolute value of the difference between the 2 heuristics H1 and H2 from the previous problems. So we can see that H4 is in fact admissible because both H1 and H2 have to be greater than 0, greater than or equal to 0 because at the goal state, both heuristics will be equal to 0. But H4 is pretty much the absolute value, the difference between the absolute value of the 2 heuristics. So that means that H4 will always be less than or equal to the maximum value of H1 or H2, depending on what's greater. And since we know that both H1 and H2 are admissible, that means that the value that H4 takes on will also be guaranteed to be admissible. Finally, H5 is the maximum of H1 and H2. And similar to the reasoning that we did for the previous heuristic, we can see that H5 is also admissible because H1 and H2 are both admissible. Moving on to part B. So we'll be picking one heuristic from part A such that we found it to be inadmissible. Let's say that heuristic is now H sub k. So we want to find the smallest constant, epsilon, such that H prime, which is the inadmissible heuristic minus epsilon, is guaranteed to be admissible. So what this means is that we want to subtract a constant value from our inadmissible heuristic, and there exists a constant value for all states, for all heuristic values, such that we can convert that heuristic given H3 to be admissible. So in order to do that, we can look at epsilon values that are greater than 0. Okay, let's start with epsilon equal to 0. If we were to set this epsilon equal to 0, then that means that h prime would still be equal to h sub k, and since we know that h sub k is already inadmissible, h prime would also be inadmissible. So let's move on to, I guess, the next possible constant, epsilon equals 1. So we can see that epsilon equals 1 works because the true cost for Pac-Man to travel to the goal state will be equal to the distance that Pac-Man has to travel to the nearest food pellet plus the distance that Pac-Man has to travel to eat the rest of the food pellets that are present on the grid. And that's going to be n minus 1 food pellets if we consider that at a current state, Pac-Man has n food pellets left. This true cost is always going to be greater than or equal to the distance to the nearest food pellet, plus the number of food pellets that would be left after Pac-Man eats that nearest food pellet. So that's why if we convert this particular statement, distance to nearest food pellet plus n minus 1 food pellets, we can see that this is pretty much going to be equal to h1, which was the distance to the nearest food pellet, plus h2 minus 1, which is pretty much the number of food pellets left at a current state minus 1 in order to account for the food pellet that was eaten. And since each food pellet is at least 1 unit away from each other, then Pac-Man has to travel at least a distance of 1 to eat the next food pellet in the sequence. And so therefore this heuristic will always be less than the true cost, which makes it admissible. So in this problem, we can say that for two heuristics, h sub a and h sub b, h sub a is going to be less than or equal to h sub b if for all possible states x, h sub a of x is less than or equal to h sub b of x. And in this case, h sub b is going to be a dominant heuristic over h sub a. So we have these boxes below to kind of just order the heuristics that we explored in the previous parts, or part A specifically, so that we can see which heuristics dominate others. And if two heuristics don't share a dominance relationship, we can put them in the same box. So basically for this problem, if we look at h sub 1 and h sub 2, we're not able to establish a dominance relationship between the two heuristics because sometimes the distance to the nearest food pellet might be less than the number of food pellets left. Like for example, consider that on a grid, Pac-Man has 3 food pellets left to eat, but it's really close to one of the food pellets, such that it's only a distance of 1 away. In that case, the distance to the nearest food pellet would be smaller than the nearest or the number of food pellets left. But then the other case could also be possible where there's only 1 food pellet left, but the distance to that food pellet is incredibly large or significantly larger than 1. Then in that case, we can't establish a dominance relationship between h1 and h2. Similarly, we can't establish a dominance relationship between h4, which is the absolute difference between h1 and h2, and h1 or h2. And this is because if we're considering that absolute difference, sometimes h1 might be bigger than h2, and other times h1 might be smaller than h2, based on our previous findings. And so in that case, h4 can never be a dominant heuristic because it's not guaranteed to be larger than either of these heuristics given here. And in the same way, it can't be smaller. And then finally, h5 is dominant over h1 and h2. And this is because we always take the max value over h1 and h2. And so either h5 is equal to h1 or it's going to be greater than h1 if h2 is greater than h1. So then in that case, H5 will always be greater than or equal to H1. And we can apply that same reasoning for H2. Okay, so moving on to part D, let H sub I and H sub j be two admissible heuristics. And we can construct a new heuristic H sub alpha, which is just the weighted sum of H sub I and H sub j. Give the range of values for alpha for which H sub alpha is guaranteed to be admissible. So if we're looking at the possible ranges, we want to have alpha be in the range 0, 1. And this is because since both H sub 1 and H sub 2 are dominated by H sub 5, then that means that the weighted sum of both H sub 1 and H sub 2 will also be dominated by H sub 5, which is the maximum value of either value heuristic. And since H sub 5 is shown to be admissible, then that means H sub alpha will also be admissible. Moving on to part E. Let's say we consider an arbitrary search problem in the graph that with start state S and goal state G. And then we can set H star to be the perfect heuristic. So H star of X represents the optimal distance from X to the goal G. We can also determine a value epsilon to be some positive number. So we're going to look at some sample heuristics, H sub A, H sub B, and H sub C, and give expressions for the range of possible values for the total cost of a path from S to G that A star tree search could return when using that heuristic. We can write our answers in terms of H star of S and epsilon. And then H sub 0 is just going to be some arbitrary admissible heuristic. So if we look at the first one, where H sub A is going to be equal to that arbitrary admissible heuristic, H sub 0, for all states, then that means that H sub A is also going to be admissible because it takes on the same values. And so we can use the fact that A star tree search is optimal with an admissible heuristic to show that since H0 is admissible, then A star will always return the path with the optimal cost. Because we have determined, or we've set the true cost to be H star of S, where S is the start state, we can see that the cost that's given by the path that A star returns will be the optimal cost. And so the min range and the max range are pretty much the optimal cost values. Next, if we look at H sub B, which is pretty much the same, very similar to H sub A, where it's equal to H sub naught for all of the states in the graph, except for one unspecified state Y, where H sub B of Y is going to be equal to the value that H naught gives you at state Y plus some arbitrary epsilon, which is a positive number. So for this case, we can consider two different paths or cases. The first case is where we look at node Y. If Y is not on the path that's returned by A star, then that means the heuristic values for all nodes on the optimal path are going to be admissible because they're pretty much equal to the value that H sub naught gives you. And in that case, A star tree search is optimal by our previous reasoning, so the path cost that is given by the algorithm is going to be H star of S. So that's our min range value. The other case is when Y is actually on the path that's returned by A star. So this happens when there are no better paths for A star to search because Y influences the optimal path. That would originally be the path returned by H naught if it wasn't changed or if that epsilon wasn't added to that particular state. So in the case where A star can find a better path, then the path cost that is returned by A star is basically worsened by that value epsilon. So it's increased by epsilon because that heuristic value pretty much influenced the path cost that was returned. So in that case, your max path cost is going to be H star plus epsilon. If there is a better path that A star can search where y isn't present, or if like A star selects a different path while comparing y to some other node, then it's guaranteed that that other node has a lower heuristic value compared to y. So that path cost will be greater than 8 star of S because that's the optimal, but here we're considering suboptimal options. But the path cost is still going to be less than the worst possible path cost, which is 8 star plus epsilon. So that's how we get our min range and max range. Finally, for 8 sub C, 8 sub C is pretty much the same thing as H naught, except we add epsilon for all of the states X. So in this case, since we're changing all heuristic values for all states by the same constant, that means that the nodes that are explored in A star are going to be explored in the same order. And since that's the case, the path that's returned by A star is still going to be the same as the optimal path. So the true path cost that A star will return will still be having the path cost of 8 star of S.